Hello. Today we're going to learn about the Laplace transform. Transform methods are heavily used in different fields of engineering, and the Laplace transform is kind of the introductory transform, although some of you may have already seen Fourier transforms in your studies. But we'll stick with Laplace transforms here. First, we need a definition. So for a function f of t defined for t positive or 0, this notation right here, L and then curly brackets with the f of t inside, this is literally stated the Laplace transform of f of t, okay? And it's equal to the infinite integral from 0 to infinity of e to the minus st times f of t dt. And the result that we get is, since we're integrating with respect to t, and e has this s in its exponential, we're going to end up with a function of s, okay? So what we're doing here is we're transforming a function that is dependent on time into a function that is dependent on a new variable, s. It turns out that this variable is technically living in the complex world, but that's not really important for understanding how to do this process, okay? E to the minus st for t greater than 0 and s also greater than 0 in this particular form right here, this is a decreasing function, right? And so as long as it decreases faster than f of t for s positive, then the overall integrand will converge in this on this infinite integral. So in Calculus 2, we learned that when we're dealing with integrals that go from 0 to infinity, we need to be very careful and take limits, because it may turn out that we get an infinite value for our integral. And so we don't want that. We should be getting finite functions, and there have to be domain restrictions that go in because of that. And so in this particular one, we have that s is greater than or equal to 0 as well, okay? Now there might be a shift in s, and that would change its domain, but this is our standard definition, okay? So this is said to be the Laplace transform of little f, provided the integral converges. Now I am going to adopt a new language of sorts where I actually focus on whether a letter is capitalized or not. So notice I said the Laplace transform of little f, and that's going to give us big F of s, okay? And you don't get to decide where little f and big F are used. That has been decided for you, okay? We take the Laplace of little f, we get back big F. The Laplace transform is called an integral transformation, and it satisfies the linearity property. And so the linearity property is something that we've been doing forever in mathematics, but you may not know specifically what it is. But the linearity property says that if you have a sum of something, then you could also look at, like, for example, if you have a sum of integrals, you could instead look at the integral of the sums, or vice versa. If you have the integral of a constant times a function, then you could pull the constant outside and say, I have a constant times the integral. And so with us, with the Laplace transform, we say the sum of Laplace transforms is the same as the Laplace transform of a sum, and vice versa. And the constant multiplier of a Laplace transform is the same as the Laplace transform of a constant multiplier, and vice versa. So I've written that out for us here. The Laplace transform of a little f of t plus b little g of t will equal a times the Laplace transform of little f of t plus b times the Laplace transform of little g of t, where I've dealt with the sums and the constant coefficients at the same time. When dealing with linear differential equations, such as the ones that we see in electrical circuits or mechanical systems like the mass spring systems, population models, and such, the Laplace transform can convert the equation from the time domain to this S domain. So we're going from T to S. And the S, it's a specific complex domain. It's the complex frequency domain. And what ends up happening is that the Laplace transform, once we get to the point where we can use the table of Laplace transforms, it ends up being an algebra problem instead of a calculus problem. And sometimes that can make it an easier problem to solve. Of course, the problems that we're going to work with in here are often easier using the calculus methods because we're just learning this process and we won't be applying it to the most difficult of differential equations. So when you are doing your homework, you will have some homework that asks you to use the definition of the Laplace transform. That means that you need to use the Laplace transform of little f of t is equal to the integral from 0 to infinity of e to the minus st f of t dt in order to calculate your big F of s. Okay? We will also have problems that say use the table of Laplace transforms, and so we'll have to learn how to use those. Now your book has derived several Laplace transforms using the definition. I would go over those carefully, maybe try them on your own, but we're going to work through a few of the more complicated ones here. So in the first example, we're asked to find the Laplace transform of f of t equals t squared. Okay, so we're looking at the Laplace transform of t squared. That's going to equal, when I use the definition, it's the integral from 0 to infinity of e to the minus st times t squared dt. Now this is an infinite integral, so technically I should be writing this as the limit as b goes to infinity of the integral from 0 to b, and I'm going to switch my order here, t squared e to the minus st dt. And that would be written correctly. Now this t squared e to the minus st, I need to use an integration by parts on that. So I'm going to go over here on the side and do that. And it looks like I'm going to have multiple integration by parts. So I'm going to set up my u and my dv columns and use tabular integration. So my first choice would be that u is t squared and dv is e to the minus st. Then I would find the first derivative of t squared, it's 2t, and I'd find the antiderivative of e to the minus st, and it's minus 1 over s e to the minus st. I would have a plus symbol on the first row, a minus symbol on the second row. Then in the second integration by parts, the second row would be my u and my dv. And so when I find my du, it's 2. And when I find my v, it's going to be a 1 over s squared e to the minus st. And then I would have my plus sign here. Then again, I'd have to do another integration by parts. And so if my u is 2, then my du is 0. And I'd have a minus sign here. And when I find the antiderivative, I get a negative 1 over s cubed e to the minus st. Okay. Now the process here is we look at diagonal products. So the first row, first column gets multiplied by the second row, second column. And then the second row, first column gets multiplied with the third row, second column. And then the first row, third column gets multiplied with the second row, fourth column. Sorry, that was wrong. Fourth row, second column. And then we do our backwards integral of. Okay, so this looks like I've got equal to the limit as b goes to infinity, and my antiderivative will be plus t squared times negative 1 over s e to the minus st. That gives me a minus t squared over s e to the minus st. And then I have minus 2t times 1 over s squared. So that'll be a minus 2t over s squared e to the minus st. And then I have plus 2 times negative 1 over s cubed. So it'll be minus 2 over s cubed e to the minus st. And then I have minus the integral from 0 to b of 0 dt, because that backwards product gives me a 0 times my antiderivative, and that's just going to be 0. So that whole thing is just going to go away to 0. All right, now this is being evaluated from 0 to b, so I plug in b and then I plug in 0. I look at the limit as b goes to infinity of minus b squared over s e to the minus sb minus 2b over s squared e to the minus sb minus 2 over s cubed e to the minus sb, and then minus evaluating everything at 0. Since I have all negatives here, when I subtract this, I'm going to get all positives, evaluating at 0. I get a plus, the t squared becomes 0. I get a plus, the 2t becomes 0. And then I get a plus 2 over s squared e to the 0. Okay. Now, if I take the limit as b goes to infinity, remember s is a positive number. And so e to the minus s infinity, that is in our denominator blowing up. And so those terms are going to 0, those e to the minus sb's and this one, all three of them. And so this finally finishes up as just 2, how did I get a 2? Yeah, 2 over s cubed, no, squared. Hang on. I see what I did wrong. When I evaluated this last term here, the 2 over s squared, that should have been 2 over s cubed. I was hesitating because I knew what I got was wrong. It was impossible for it to be 2 over s squared. It needed to be 2 over s cubed. All right, found my issue. There it is. All right, so the Laplace transform of t squared is equal to 2 over s cubed. So we did a lot of work to get a simple answer, but this is our big F of s. Okay, let's try another one. I chose a couple of problems that would force us to do a lot of integration by parts, because that is sometimes a tricky topic for people. And some of the trickier integration by parts come up quite often in here. So I want to make sure to go over them in a video. All right, we have f of t as cosine of 3t. We're supposed to find big F of s. So we're looking at the Laplace of the cosine of 3t. That will be equal to the, I'm going to go ahead and write it as the limit as b goes to infinity, the integral from 0 to b of e to the minus st times cosine of 3t dt. All right, I got to do an integration by parts, and I've got to do multiples of them. And this one is actually going to bring up the circular integration. So let's see what that means. Whenever you have the exponential is always the dv. So that means cosine of 3t will be our u, and e to the minus st will be our dv. Technically, you could do it the other way around, but I promise you, it's not going to give you what you need. Okay, so I'm giving you the advice. Make sure that e to the minus st is your dv. All right, and the first row is positive. Okay, so if I'm going to go ahead and take care of all my derivatives and then take care of my antiderivatives. So the derivative of cosine of 3t is going to be a minus 3 sine of 3t. And then the next derivative will be a minus 9 cosine of 3t. And that will be as far as I have to go. So my signs here are minus and plus. The first antiderivative of e to the minus st is minus 1 over s e to the minus st. The next one is 1 over s squared e to the minus st. Okay, we have our diagonal products twice, and then we're going to go back. The reason I chose to stop at row 3 is because I can see that aside from the 1 over s squared and the minus 9, that product in an integral is exactly the same as what I started with, e to the minus st cosine of 3t. And that's what I'm looking for when I do circular integration, because I'm going to add that over to the left-hand side. So let's write this out. Okay, what we have here is this is equal to the limit as b goes to infinity of negative 1 over s e to the minus st cosine of 3t. It's my first diagonal product. My second diagonal product is minus a negative, and so that'll be plus 3 over s squared e to the minus st sine of 3t. And then plus, there's my circled plus, the integral of the backwards product, and so that has a negative sign in it. It'll be minus 9 over s squared times the integral from 0 to b. I have my limit outside, so that's good. And I have e to the minus st cosine of 3t dt. Let me see if I can move just that down a little bit. There we go. Okay. And then these first two terms can be evaluated from 0 to b. And that last term is just tucked away off to the side a little bit. Okay, so what I'm seeing here is that this integral right here, this is just the Laplace of cosine of 3t. Just look up here and we can see that, okay? So I'm going to move it over to the other side. And what I mean by that is the other side has the Laplace of cosine of 3t already. So I'm going to add plus 9 over s squared times the Laplace of cosine of 3t, just moving it over to the left. On the right, I keep what was there. I have the limit as b goes to infinity of the minus 1 over s e to the minus st cosine of 3t plus 3 over s squared e to the minus st sine of 3t from 0 to b. So I didn't evaluate my antiderivatives at 0 and b. I just wanted to do one step at a time right there, where we are just dealing with adding that extra integral over to the left-hand side. Now, on the left-hand side, I have one of these Laplace transforms and 9 over s squared of these Laplace transforms. So I have 1 plus 9 over s squared times the Laplace of cosine of 3t is equal to the limit as b goes to infinity of, now evaluate the the functions at b. So we have minus 1 over s e to the minus sb cosine of 3b plus 3 over s squared e to the minus sb sine of 3b minus, and the first term is negative, so it'll be plus 1 over s e to the 0 cosine of 0 is 1, and then minus 3 over s squared e to the 0, and sine of 0 is 0. So that's going away. Okay. All right. On the left-hand side, I need a common denominator. It's s squared. So this becomes s squared plus 9 over s squared times the Laplace of the cosine of 3t. And on the right-hand side, we go ahead and evaluate the limit. Now the e to the minus sb as b goes to infinity, that's going to 0. The cosine is just waffling. It's waffling between minus 1 and 1. The next one, the sine term that has the e to the minus sb, that also goes to 0. And then we have just one little term left right here that's non-zero. Everything else goes to 0. So on the right-hand side, we just have 1 over s. And so then we go ahead and multiply by the reciprocal of s squared plus 9 over s squared to get Laplace of cosine of 3t is equal to 1 over s times s squared over s squared plus 9. The s in the denominator simplifies with the s squared on top. And so this becomes s over s squared plus 9. That's our big F of s. Okay, that's a lot of work. And you may have forgotten about the circular integration, but hopefully you remember it now and practice it a little bit so that you're used to it. It's not uncommon to see it. We'll see it in homework, see it in, if you take quizzes, you may see it in quizzes, you might see it in exams. Be prepared. You should know how to use all the methods of integration you've learned. All right. We may also see piecewise functions. So electrical systems may be run by a piecewise function. For a certain period of time, a system is turned on in a certain way, and then after that period of time, it's turned on in a different way. So in this case, I'm asked to find the Laplace transform of f of t, where f of t is equal to t when t is between 0 and 5, and f of t is equal to e to the 2t when t is greater than or equal to 5. Now, I kind of wish I had chosen a number like 6, because my 5's and my s's are sometimes very close. So I'll do my best to tell them apart. All right, the Laplace of f of t in this case, it can be confusing because you're like, well, which function do I choose? Both of them for different time periods. Okay, so what this means when we have a piecewise function is that the piece that deals with t going from 0 to 5, that's going to be the integral from 0 to 5 of t e to the minus st dt. And then plus, we pick up the next piece, and we're going to start at 5 and go to infinity. So I'll do the limit here. The limit as b goes to infinity of the integral from 5 to infinity. Sorry, to b. And this one will be e to the 2t times e to the minus st dt. I want to do something over here real quick. So if I have e to the 2t and e to the minus st, this is equal to e to the 2t minus st. I want this written where the minus comes first and the s comes before the 2. So this would be written as e to the minus st plus 2t. And now I will factor out a minus sign. This is e and a t. This is a e to the minus, inside is an s minus 2, and then outside is a t. So that's how I'm going to rewrite my exponential. And my reason for this has to do with the way the table calculations are set up. It also has to do with making things a little bit easier for me to see, like domain things. So I want the minus outside so that I know that s minus 2 has to be positive or equal to 0, which means s has to be greater than or equal to 2. It's a little bit easier for me to see it that way. And this just ensures that we have a convergent integral. If we don't have that, then we don't know that for certain, okay? All right, so let's go ahead and rewrite one time, and then I'll deal with my integral. So we have the integral 0 to 5 of t e to the minus st dt plus the limit as b goes to infinity of the integral from 5 to b of e to the minus, in parentheses, s minus 2 times t dt. Okay, now I have an integration by parts in the first integral. And it's not a horrible one, so I won't use tabular integration, but I do have u is equal to t, dv is equal to e to the minus st, du is then just dt, and v is a minus 1 over s e to the minus st. So then uv would be minus t over s e to the minus st minus a negative, so it'll be plus 1 over s times the integral of e to the minus st dt. And then that just integrates one more time, And we get minus t over s e to the minus st, and then a minus 1 over s squared e to the minus st. All right, that's the value of our antiderivative in the first integral. So I get minus t over s e to the minus st minus 1 over s squared e to the minus st, evaluated from 0 to 5, plus the limit as b goes to infinity. Now when I integrate e to the minus s minus t 2 all times t, the minus and the s minus 2, those are all just constants. Remember, if we're integrating an exponential function, we just divide by the multiplier with the t. So this becomes a minus 1 over s minus 2 e to the minus s minus 2 times t, evaluated from 5 to b. Okay. In the first set, when we're evaluating from 5 to 0, we get minus 5 over s e to the minus 5s minus 1 over s squared e to the minus 5s minus a negative 0 minus a negative 1 over s squared e to the 0. Okay, that takes care of the first antiderivative. The second one, we still have plus the limit as b goes to infinity. When we evaluate t at b, we have minus 1 over s minus 2 e to the minus s minus 2b. And then we have, I think I need to move this down a bit so it doesn't run into my integration by parts. All right, and then we have minus a negative, so it's plus 1 over s minus 2 e to the minus of s minus 2 times a 5. Okay. All right. Let's rewrite everything so it looks a little bit better. Okay, we've got a minus 5 e to the minus 5s over s minus e to the minus 5s over s squared plus 1 over s squared. And then as b goes to infinity, this first term goes to 0, and the second term is not affected by the limit. It is just plus e to the minus 5 times s minus 2 over s minus 2. And that is the final answer from having taken the Laplace transform of this piecewise function. Okay, that was a lot of work, which means there's a lot of room for error. I'm only happy with my answer because when I worked this out on paper beforehand, I got the same thing. So I got it twice. I was not referring to my work, so I'm pretty sure it's good. But you know, this is kind of how it is. You do your best, and then if it's not the right answer, you try to find the mistake. Okay. In the problems that ask you to use the definition of the Laplace transform to evaluate, it is expected that you will use this process. Okay? Otherwise, you'll be the instructions will say, use theorem 7.11. Really, use the Laplace transform table. It's at the back of your book, or you can find one online. I believe I should have one in the formula sheet in our learning management system, but there are lots of places you can get the table of Laplace transforms. Okay, check with your teacher. If you're not in my class, check with your teacher that whether you'll be able to use the table of Laplace transforms. My students definitely get to use it. Okay, so using the table for Laplace transforms. In your book, they're asking you to use theorem 7.11, and it just has like 5 Laplace transforms, or 7. And I'm giving us 5 here. So the Laplace transform of 1 is equal to 1 over s. Just remember that this would come from the integral from 0 to infinity of 1 times e to the minus st dt, right? And this second one, if we get the Laplace of t to the n, it's n factorial over s to the n plus 1. That's just looking at the integral from 0 to infinity of e to the minus st times t to the n dt. Okay, so each of these big F of s's that we have here are based on evaluating some infinite integral, which as you do the homework, you'll find it gets to a point where it's too cumbersome to keep going. And that's why we have the table. So the Laplace transform of e to the at will equal 1 over s minus a. If a was like a positive 2, then that would be e to the 2t that we're taking the Laplace transform, and it gives us 1 over s minus 2. But if it was like e to the minus 3t, then we have a minus sign for a, and so it's 1 over s minus a negative, so it would be s plus 3. So just pay attention to how the signs work out. The Laplace transform of sine of kt, where k is just some number, is going to give us k over s squared plus k squared. And the Laplace transform of cosine of kt is equal to s over s squared plus k squared. We actually did the cosine of 3t and got s over s squared plus 9. So the work was good there. Now, for anybody who doesn't know, the exclamation point on a number just means take that number and multiply it by every number, whole number less than it until you get to 1. So for example, 4 factorial is 4 times 3 times 2 times 1, which is 24. Okay. Now let's see how we can use these Laplace transforms from a table in a few examples. So find the Laplace of little f of t using linearity and the list of Laplace transforms. So the linearity means we're going to distribute the Laplace transform across this sum, and we're going to pull constants out in front. So the Laplace of 5t cubed minus e to the 7t plus 13 is equal to 5 times the Laplace of t cubed minus the Laplace of e to the minus 7t plus 13 times the Laplace of 1. And then I can identify the functions that I'm dealing with. I can identify them in my table up there. So t cubed, go to number 2, t to the n, so n is 3. That means we should get 3 factorial over s to the 3 plus 1, that's going to be 4. Okay, minus the Laplace of e to the minus 7t, that's number 3. So a is minus 7. That means we get minus 1 over s minus a negative 7. And then plus 13, and then the Laplace of 1 is 1 over s. Okay, so just cleaning that up a little bit. 3 factorials, 3 times 2, which is 6, times the 5 gives me 30 over s to the 4th, minus 1 over s plus 7, and then plus 13 over s. That's our final answer for that one. And that's our big F of s. So that's a lot easier than having to use the integrals. We like the tables. They make things a lot easier. But sometimes our functions get to be a little bit more complex. And so here we have the Laplace of minus 3 times the quantity of t plus 1 squared, minus 6 cosine of 2t, plus 4 sine of 9t. So what I need to do is I'm going to distribute, but I'm going to be very careful because that t plus 1 all squared, I need to FOIL that out. Okay, so I'm going to do this in a multi-step process. So this is equal to the Laplace of minus 3 times t squared plus 2t plus 1. That's what I get when I square t plus 1. I'll close that. Minus 6 times the Laplace of cosine of 2t plus 4 times the Laplace of sine of 9t. Okay. Now that minus 3 will distribute to the t squared, the plus 2, and the plus 1. And so I'll distribute and pull out at the same time. So it's minus 3 Laplace of t squared. And then the minus 3 and the 2t gives me minus 6t. So I get minus 6 Laplace of t. And then I get minus 3 Laplace of 1. And I still have my minus 6 Laplace of cosine of 2t plus 4 Laplace of sine of 9t. Okay, so the t squared, that's going back to the t to the n. So I get n factorial over s to the n plus 1. So it's minus 3 times 2 factorial over s to the 2 plus 1, that's 3. Minus 6 t to the 1, it's going to give us 1 factorial over s to the 1 plus 1, which is squared. And then minus 3, the Laplace of 1 is 1 over s. Okay, minus 6, the Laplace of cosine of 2t, the multiplier is 2, and so we'll get s over s squared plus 2 squared. Okay, and then plus 4, Laplace of sine of 9t. Sine, the multiplier is 9, so I should get 9 over s squared plus 9 squared. Okay, and now I just got to simplify this. 2 factorial is just 2 times 1, and that's 2, times the minus 3 outside gives me negative 6 over s cubed, minus 6 over s squared, minus 3 over s, minus 6s over s squared plus 4, plus 36 over s squared plus 81. That's our big F of s. And that would have been really, really horribly painful if we had had to use the definition to come up with the value of that Laplace transform. So the table's pretty powerful. It's like our best friend when we're dealing with Laplace transforms. So make sure to really practice these, and then soon we'll use the Laplace transform to solve differential equations. But first, get comfortable using it. As always, if you have any questions, please reach out.